Hi, everyone. Thank you for joining this talk, where I will show recent highlights on extragalactic magnetism using far-infrared polarimetry. This is part of a SOFIA legacy program where we combine far-infrared radio and radio polarimetric observations with gas dynamics of the neutral molecular gas. We know most of our knowledge from extragalactic magnetism arises from radio polarimetric observations, where we know that spiral galaxies show this large scale order B field, where it contributes from order and turbulent fields along the spiral arms. For H-on galaxies, we have this X-shaped structure underlying feature of spiral galaxies that extend several kiloparsecs into the halo. And then when we go to irregular galaxies and interacting galaxies, we have a combination of the alpha omega mechanism operating, and also the gas measures make the B field become more aligned along the compression front or perpendicular to velocity gradient, that make the average B field to be slightly stronger than the typical in spiral galaxies. The definitions are very common here in this field. So the total intensity synchrotron emission trace the total B field in the plane of the sky, where we can estimate the magnetic field strength and sensitive to the strength of the magnetic field and the cosmic ray electron density. The polarized intensity trace the order B field in the plane of the sky, and then we can trace the orientation of the magnetic field, where the direction of the magnetic field can be estimated using Zeeman effect of Faraday rotation. The polarized intensity of the synchrotron emission is sensitive to the B field geometry, and also the polarized intensity depends on the strength and the geometry of the magnetic field and the cosmic electron density. Let's record that anisotropic turbulent field and regular field contributes both to the order field. So what do we have now that is new? So here I show a polarized intensity as a function of the wavelength. You see on the right, the radio polarimetric observation is dominated by synchrotron polarization. There was some attempt a few decades ago to estimate the signature of magnetically aligned gas grains in the optical and near infrared. However, these wavelengths are dominated by the electron and dust scattering, as I show in this plot. So the sweet spot to estimate magnetically aligned dust grains turns out to be within the 100, more or less at the 100 microns regime, and this is where the molecular clouds and star formation regions peaks in their thermal emission, and this is where our observations are based. So we use a HAWK Plus, the High Resolution Airborne Waveband Camera Plus, on board of the Stratospheric Observatory for Infrared Astronomy. And we perform imaging polarimetric observations of 4 different bands: 53, 89, 154, and 214 microns. The idea behind that is that we are tracing the dust grains that are magnetically aligned with the local magnetic field in the diffuse and dense ISM. So for polarized emission in the far infrared, we have the position angle of polarization is perpendicular to the local magnetic field. This is because the long axis of the dust grains are aligned perpendicular to the direction of the field. So then when we do far infrared polarization observations of galaxies, we can rotate by 90 degrees the position and polarization, and we have the orientation of the magnetic field. This is a talk by Trump, where he's gonna show more about this mechanism. So then when we compare the definition of magnetic field components with the synchrotron and the thermal emission, we know that the total intensity of thermal emission trace the dust grain emission, but doesn't really trace the magnetic field strength or geometry. So the polarized intensity is sensitive to the geometry and the alignment of the dust grain, but it's independent of the magnetic field strength. So then what we can do is to use the orientation of the magnetic field to estimate the order B field in the plane of the sky. One interesting thing is that radio and far infrared observation trace different galactic scale heights. So in radio, the column density of electrons that we are tracing is along a scale height of 1 to 2 kiloparsec, while for far infrared in the same galaxy, NGC A92, A91, the scale height is 500 parsec. So here is telling you that the magnetic field that we trace with the far infrared is specifically from the midplane, in the midplane of the galaxy, and we don't have the potential contamination from the halo. And this is mainly the instrumental setup that we want to do in order to answer some of the key science topics of the legacy program. One of them is for active galaxies, is how the active galactic nuclei modify the magnetic field affect the magnetic field in the host galaxy. So the second one is star formation, how the star formation in the galaxy amplify and modify the magnetic field in the host galaxy. So we want to provide far infrared polarimetric observations of around 15 spiral galaxies in order to provide constraints in between the diffuse ISM traced by radio and the dense ISM traced by far infrared that can help and support galactic dynamo theory development. We have a few interacting galaxies where we trace and resolve the magnetic field in the host galaxy up to a few kiloparsec in order to estimate what is the relative contribution of the turbulent B field with regular B field, for example, here in Centaurus A. And we have a few starburst galaxies that have been surprising lately because the magnetic field that we trace are not parallel to the disk of the galaxy, but are parallel to the galactic outflow. What we found is that the turbulent kinetic energy and the turbulent magnetic energy are closing equipartition in the center of the galaxy. We make the magnetic field dynamically important. And also what we found using solar physics techniques and interpolation procedures is that the magnetic field lines are open into the intergalactic medium, which may help to enrich the intergalactic medium with magnetic field that is stronger from that of early times in cosmological scales. So what we have is a galaxy sample of around 20 galaxies. All these galaxies have available radio polarimetric observation, molecular neutral gas maps, and Herschel observations. What we offer here is far infrared polarization observations of nearby galaxies. As you see, they're interacting spiral galaxies and starbursts and some AGN with a resolution of 5 arcsecond to 18 arcsecond, depending if you are in band A, 53 microns, on band A, 214 microns. All data is available at SOFIA archive, the raw and science-ready data. But our legacy program provides high-level data products in all these radio gas tracers, Herschel, and far infrared, where you can find it here in galmax field.com. Here, what you see also, what you can find is Python code that where you can reproduce the analysis that we are doing. So as always, so this is impossible without the amazing team that we have in the legacy program. So Sui and Mao and me are the co-PI, and you see here the list of the rest of the team, where the underlying names are the people in the program. So in the workshop, where you can talk with them and go and see their talks. So the open question that we want to answer with this legacy program is how did the evolution of galaxies emerge affect magnetic fields? Is the circumgalactic medium magnetized, and how it gets magnetized? How does the multi-phase ISM affect the galactic magnetic fields? What is the structure of the magnetic field around active galactic nuclei, and how the AGN affect the magnetic field in the host galaxy? And how does the galactic B field align the dust grain in the arms and interarm? So some of these questions are already answered in several papers. For example, you can see that Centaurus A show a higher relative contribution of turbulent B field. The MD2 that I showed before is a multidisciplinary work between solar physicists and extragalactic astronomers, where we show that the galactic alpha are able to drag the magnetic field from the disk of the galaxy towards the intergalactic medium. And then I invite you to go and check the talks by Alex, where he's gonna show the recent results of the comparison between radio and far infrared in M51, where he showed that the both wavelength range doesn't really trace necessarily the same magnetic field. Lucas Grosset is gonna show the very complex magnetic field structure as a function of the spatial scale and multi-wavelength analysis in the Circinus galaxy. Tran will show how can we apply RATs, the radiative alignment torques of magnetic of dust grain alignment, in order to explain some of the results that Alex and Lucas are obtaining. So as general, so this is the few key science topics of the legacy program I showed you before, and stay tuned for more results, because we are planning for a first data release at the beginning of next year, where we're gonna show the results of 12 new galaxies observed with far infrared polarimetric observations, and all the combination with the radio and the gas tracer afterwards. So thank you so much, and let me know if we can have a further discussion about details of all this work.